carefully read at the way to understand why we are doing this before I'm going in depth. Well, Pki certificates are everywhere in OpenShift, and they are here for two reasons. Reason number one is to prove identity. Reason number two is to provide encryption. And to secure resources, in particular routes, it's essential to understand how certificates are working. Now, in certificates, there are two parts that play a role. Or I should say in Pki infrastructure, because that is what we are talking about, the public key infrastructure. In the public key infrastructure, there's the public key and the private key. The public key is what is going to be handed out to users. So if a user wants to make a request to a server, and I'm calling it user just to make clear how it is working, if a user wants to make a secure connection to a server, the user is using the public key to encrypt the traffic that is going to be sent to the server. In order to make sure that this public key is trusted, it needs to be signed by a certificate authority. The certificate authority allows the client to recognize that the certificate really is legit, and that allows the client to continue. Apart from the public key, there is the private key. The private key is kept as a big secret by the server because that is what is needed to decrypt traffic that is used on the server. So public-private keys have two purposes. Purpose number one is to provide encryption. Purpose number two is to prove identity. So how does that work? Well, in the initial TLS handshake, where the client is establishing contact with the server is sending a token that is encrypted with the server private key. And if the user can decrypt it with the server public key, then that is mathematical proof that the server is legit. And then the client knows, okay, this is legit, we can continue, and everything is good. But again, it is essential in this procedure that the public keys that need to be handed out to the client are guaranteed, and the guarantee is done by the certificate authority. Normally, the certificate authority is something external, like VeriSign, for instance. And these external certificate authorities are widely known, and nobody will doubt anything that has been signed by an external certificate authority. But the unfortunate thing is that in order to have your stuff signed by the external certificate authority, you need to pay them money and you depend on an external entity. In some cases, you are just going to use the certificates internally. And if you are only going to use the certificates internally, you can use the so-called self-signed certificate. Self-signed certificates are an easy way to get started with your own certificates. Now, self-signed certificates in the world of internet are not a very good idea. Let me give you an example. Some time ago, I was trying to make a booking at a hotel, and at the moment they were asking for my credit card details. I got an invalid certificate. Well, if I am about to enter my credit card details and I get a certificate error, then I'm out of here, because really this needs to be 100% secure. But in the world of OpenShift and internal private cloud environments where you want to have security inside, self-signed certificates might not be that bad because you are in a trusted environment. And the entire idea about a self-signed certificate is that the issuer of the certificate needs to be known to all the parties that are involved. And if you have full control over everybody who is involved in the communication, then self-signed certificates might be an option. Anyways, in the exam, self-signed certificates are the thing that you are going to use. So these self-signed certificates are configured in OpenShift resources like the routes or in the applications. And that is what I'm going to show you, because let me repeat it, depending on the way how you want to secure traffic, you are either going to configure your certificates in the application or in the route. Let me demonstrate. Folks, here's what I'm going to do. I am going to work through this demo. in two different steps. First, I'm going to send you the entire demo with some comments. Then I will zoom into the part understanding what you do. That's 4 different slides with explanation of all the different options that we are using. And then there's the last step, how to remember all of this on the exam. Because I know that if you look at commands like you see on the slide right now, nobody is capable of remembering commands like this. So let me demonstrate. OpenSSL because it already existed and I want to create a new directory. So mkdir OpenSSL. And then I'm changing into the directory because really we are going to create a couple of files, and these files just need to be in the OpenSSL directory. The OpenSSL command is how we are going to do that. So if you use tab completion on OpenSSL, then you can see that within OpenSSL there are different subcommands available, and it's the subcommands that really matter. There is 3 of them. We have genRSA, we have rec, we have x509. GenRSA is a generic command that you are going to use to generate an RSA certificate pair. Rec is for requests. That is where the client is going to communicate to a certificate authority to get the certificate signed. X509 is what you are going to use on the certificate authority. So this is what you need to remember. You need genRSA, you need rec, you need x509. And sure, instead of genRSA, you can use genDSA if you have a good reason to prefer DSA over RSA. I'm not going to make it more complicated than it is. I think you should already be quite happy if this genRSA is going all right. So OpenSSL genRSA with a couple of options, --3. That's triple dash. Triple dash is an encryption algorithm. Then myca.key as out in 2048. So what is this doing? This is generating a key, a private key. So genRSA is generating the key using the triple dash algorithm using 2048 bits encryption, and the result is written to myca.key. Then I need a passphrase for myca.key. Well, as this is the certificate authority, we really need the passphrase. You can see what's happening here. I'm pressing enter, and while I press enter, I get a complaint that the passphrase is too short. So you really need to provide something. The thing is that we are creating the certificate authority private key here, and the certificate authority private key is really an essential chain, an essential element in the security chain. And if it gets compromised, all the keys that it has ever issued will get compromised as well. So the results of a compromised certificate authority key are huge, and that is why we need a passphrase. Next, we need OpenSSL rec. So we are going to do a request -x509 -new -no dash -key myca.key -sha 256 -days 3650 -out myca.pam. Now, what is this command? Let me first press enter to see that it is working successfully. This command is what is generating the public key certificate for this certificate authority. And in order to do so, it's going to request a lot of information. And this information is just to increase the level of trustworthiness for the end user. So I can enter a country name and a state or province. I don't want to do state or province, or a locality name, or an organization name, or an organizational unit, and a common name, and an email address, and I can present anything that I want. Now, in the self-signed certificate authority, this is not really essential, because the self-signed certificate authority is supposed to be used in your internal infrastructure only. So you don't care about its security too much, about its identification too much, is what I want to say, because you're in a trusted environment. It would be completely different if you are setting up your own certificate authority. Then you really want to make sure that the entire world is capable of verifying that this one is legit. At this point, I have two files. I have myca.key. That's the certificate authority key. I have myca.pem, which is the public key certificate that was derived from the myca.key. And this myca.pem is self-signed, because we have this rec -x509. The -x509 is addressing the certificate authority functionality. We have put in the myca.key. We have applied some algorithm to it, and we have produced the output myca.pem. So the PEM file in this case, PEM is just one of the formats that you can use for a certificate authority. This PEM file is the output, and it is derived from the private key. As I said earlier, the public key is mathematically related to the private key. Also notice -days 3650. -days 3650 is the validity of the certificate authority public key. And certificate authority public keys should normally be valid for a long, long time. 10 years is not uncommon, because it should outlive the validity of any certificate that has been signed by the certificate authority. Let's face it this way: if you create a certificate authority, you have a validity of 10 years. Your certificate authority is going to sign public key certificates with a validity of 5 years. Well, you need these 5 years to be fully covered by the validity of the certificate authority public key, because otherwise your server that is using a public key certificate, which is signed by the certificate authority at some point in time, might be using a public key that has an invalid signature that has expired, and that's why what you want to avoid. And that is why normally these certificate authority keys are valid for a very long time. Then we have the next part, and that is where we are going to create the certificate. So at this point, you have the self-signed root CA certificate. Now you are going to create a certificate, and that is what we are going to do now. So open SSL gen RSA -out tls.key 2048. TLS.key is kind of a standard name in RSA certificates. I'm not using the triple dash encryption here. It's just the simple way to generate a private key. That's also why it's not asking for any password whatsoever. We just want to keep it simple. Now again, I have just generated a private key, and this private key needs to be signed. And it needs to have a public key extracted, and that's what we are going to do next. So open SSL rec for request, -new, so we have a new request, -key tls dot key, and now we go for a different approach, -out tls.csr. Now what is a CSR? A CSR is a certificate signing request. And this certificate signing request is a package that you are going to send to the certificate authority. So how does that work? Well, I am going to enter the certificate signing request, and in the certificate signing request, I am going to use everything that needs to be used. So the country name, the state or province, the locality, the organization, the organizational name. Most important is the common name. Now I've made a note about the common name on the slide, and let me see. The common name on the slide is lingnx-myproject.apps.crc-crc.testing. What is this common name? Well, later you are going to use this public key certificate on a route. This route is generating a host name. And the common name that you put in this public key certificate must match the host name. Because if it doesn't match the host name, the client will refuse connection. Now, if you are working in a browser, then you can easily tell your browser client to stop whining and to accept it anyway. But if you are using a command line client, which we are going to do in OpenShift, OpenShift does not have a stop whining and do it anyway button. You really need to make sure that everything is all right. So the name that you are entering here is very important. lingnx dash my projects dot apps dash crc dot testing. I'm double checking. lingnx dash my project dot apps dash crc dot testing is doing it, and that is enough. And I don't want anything else. Everything else is optional. You should know, by the way, before I'm continuing, one more part of information that is interesting is this name. The name that it's asking for here is a typeful LDAP name. And if I would like to provide the typeful LDAP name, then it looks something like CN is lingnx-my project dot apps dash crc dot testing, comma. O is MyCorp, comma. L is Amsterdam, comma. C is NL, something like this. If on the exam you see such a typeful name, including the CN and the O and the L and the C stuff, that refers to the questions that you are asked for while generating this public key certificate. So make sure you know that these do match. On the exam, it is not completely impossible that you need to enter this information. So now, at this point, where are we? We are at the point that I have my TLS key. The TLS key is what is going to be used by my application. I also have my certificate signing request. The certificate signing request is ready for signing. We now need to send it to the certificate authority to get it signed. And that is the last step. And how are we doing that? Well, OpenSSL X509 minus rec. So we are addressing the certificate authority functionality, minus rec for the request, minus in tls.csr. So you put the certificate signing request in, minus CA. And we need to identify the certificate authority, minus CA, myca.pem. So this is the PEM file, which is the public key of the certificate authority that you are going to use for signing. Minus CA key, which is myca.key, minus CA create serial, minus out, tls.crt. That's a certificate that I want to generate, minus days 1650 and minus SHA 256. So this is what is generating the signed certificate. So I need to enter a passphrase for myca.key because this is secure business and it's only going to work if we enter the passphrase. And then the result is here. And in this result, you can see that I have a tls.crt, a tls.csr, and a tls.key. And these are what we are going to use inside our application. The myca.key, the myca.pem are only used in the process of signing your end user certificates. And then there is a myca.srl. The .srl is the serial file. And the serial file is how a certificate authority is keeping track of all the signing actions that it is doing. Okay, I hope this already makes a little bit of sense. I'm going to continue, and I want to tell